Next, we turn to actuation and testing.
I'd like to introduce actuator sizing. Actuators are selected by matching the force required to stroke the valve with an actuator that can supply that force. For rotary valves, a similar process matches the torque required to stroke the valve with an actuator that can supply that torque. This fundamental process is the same for pneumatic, electric, and electrohydraulic actuators. The force required to operate a globe valve consists of 4 components. First, the force to overcome static unbalance of the plug. Second, the force to provide a seat load. Third, the force to overcome packing friction. And fourth, additional forces required for certain specific applications or constructions. Therefore, the total force required is expressed as the sum of A, B, C, and D. A table is also provided showing the area by port diameter, which serves as the basis for calculating the unbalanced force in term A, a quarter inch, is 0.028, March 8th in, is 0.110, 1/2 in, is 0.196 and 3/4 in, is 0.441 SQ in. Continuing on, 1 and 5/16 in, is 1.35, 1 and 7/8 in, is 2.76, 2 and 5/16 in, is 4.20, 3 and 7/16 in, is 9.28 and 4 March 8th in, is 15.03, with large ports listed up to 38.48 and 50.24 SQ in.
I'd like to introduce the calculation of term, the unbalanced force, which is the first component of the actuator operating force. The unbalanced force is the force resulting from fluid pressure at shutoff, and in the most general sense, it is expressed as the net pressure differential multiplied by the net unbalance area. The net pressure differential is typically taken as the maximum upstream gauge pressure, unless the process design always ensures a back pressure at the maximum inlet pressure. In a single-seated flow-up design, the net unbalance area refers to the port area. Depending on the configuration, the stem area may also need to be reflected in the unbalance area. Even for balanced valves, they're not perfectly balanced and a small unbalance area remains. So this value should be verified using manufacturer data. The text provides a table of representative unbalance areas for single-seated unbalanced valves and balanced valves in a flow-down configuration.
I'd like to introduce the seat load requirements that determine valve shutoff performance. Seat load is expressed as pounds per lineal inch of port circumference, and a higher leakage class requires a larger load. Class 1 follows user specifications and requires no factory leak test. Class 2 applies 20 pounds per inch of port circumference, and Class 3 applies 40 pounds. For Class 4, based on a standard lower seat, 40 pounds per inch is given if the port diameter is 4.385 inches, or less, and 80 pounds if it is larger. For Class V, in the case of metal seats, the load is determined by reading the Figure 5.3 graph, and separate recommended values are used for optimum performance and life in boiler feedwater service. Class 6 metal seats require the largest load at 300 pounds per inch of port circumference. This table is based on ANSI/FCI 70 to 2 and IEC 60534 to 4 leakage class standards.
I'd like to introduce the force that actually creates the seat load. The seat load is determined by shutoff requirements and is usually expressed as pounds per lineal inch of port circumference. This load is one of several thrust components that the actuator must supply when closing the valve, and a larger value is required as the shutoff requirements become more stringent. In particular, for Class V metal seats, the load is calculated separately to achieve optimum performance and seat life in boiler feedwater service.
I'd like to introduce the criteria used to determine the required seat load. The seat load starts with the shutoff requirements, and factory acceptance tests follow the ANSI/FCI 70-2 standard and the International IEC 60534-4 standard. This applies to leakage classes from Class 2 to Class 6, and the recommended seat load is determined by referring to the table seen previously.
I would like to introduce the precautions when applying leakage classes and packing friction, which is another component of thrust. First, because the severity of service conditions varies, leakage classes and their corresponding leakage rates should not be interpreted as direct indicators of field performance. To prolong seat life and shutoff capabilities, use a seat load higher than the recommended value. Please refer to Figure 5.3 for suggested seat loads. Conversely, if tight shutoff is not the primary consideration, it is reasonable to select a lower leakage class. Packing friction is determined by stem size, packing type, and the compressive load placed on the packing by the process or bolting. However, packing friction does not exhibit 100% repeatable characteristics, and significantly high friction forces can occur, especially in live-loaded designs using graphite packing.
I will now introduce typical packing friction values based on stem size and additional forces. This table is organized by stem size and applied class, with stem sizes categorized as 5/16 in, 3/8 in, 1/2 in, 5/8 in, 3/4 in, and 1 1/4 in. The values shown are the frictional forces typically encountered when applying standard packing flange bolt torquing procedures. Separately, under item D, there are additional forces. These are forces required to stroke the valve, such as bellows stiffness, unusual frictional forces from seals, or special seating forces for soft metal seals.
I will explain the friction values by packing type and how to reflect additional forces. The packing friction table is divided into PTFE packing and graphite ribbon or filament packing, and each is further categorized into single and double configurations. A value such as 112.5 in the table represents the friction force for that specific stem and packing combination. Additional forces refer to the extra force needed to move the valve, such as friction from seals or special seating forces for soft metal seals. These values should be provided by the manufacturer or taken into account when sizing an actuator.
I will explain how to calculate the force generated by a pneumatic diaphragm actuator. The net output of the diaphragm type is categorized into two cases. In an air-to-close configuration, the additional air pressure applied after compressing the spring creates the net output, and in an air-to-open configuration, the net force from the precompression of the spring creates the net output. This force is calculated by converting how many pound force are produced per 1 sig of differential pressure. Let's look at a specific example. Suppose that as a result of the calculation using the procedure described earlier, 275 lbf is required to close the valve. In this case, one available option is an air-to-open actuator with a diaphragm area of 100 square in and a bench set of 6 to 15 sig. The expected operating range is 3 to 15 sig. Precompression is calculated as the difference between the lower end of the bench set, 6 sig, and the start of the operating range, 3 sig, which results in 3 sig. Since this 3 sig is used to overcome the precompression, the net precompression force is 3 sig multiplied by 100 square in, which is 300 lbf.
Since the 300 lbf calculated in the previous example exceeds the required 275 lbf, it can be seen as a sufficient and appropriate selection. Piston actuators with springs are sized in the same manner. However, the thrust of a piston actuator without springs is calculated more simply as the piston area multiplied by the minimum supply pressure to find the available thrust. It is important to ensure that unit consistency is maintained here. Meanwhile, if an actuator supplies too much force, problems may arise. The stem could buckle, bend enough to cause a leak, or valve internals could be damaged. This occurs when the actuator is too large, or the maximum air supply exceeds the minimum air supply available. Typically, the manufacturer is responsible for actuator sizing and should have documented methods to check for maximum stem loads. Manufacturers also publish data on actuator thrusts, effective diaphragm areas, and spring data.
Now, I would like to introduce how to size an actuator for a rotary valve. When selecting the most economical rotary valve actuator, the determining factors are the torque required to open and close the valve and the torque output of the actuator. This method assumes that the valve has already been properly sized for the application, and that the application does not exceed the pressure limitations of the valve. The torque of a rotary valve is expressed as the sum of several torque components. However, to avoid confusion, some of these components have been combined and some calculations have been performed in advance. As a result, the torque required for each valve type can be represented by two simple and practical equations. First is the breakout torque, where TB equals A times the shutoff pressure plus B. Second is the dynamic torque, where TD equals C times the effective pressure. The A, B, and C factors for each valve design are summarized in the following tables, with the valve shaft appearing as a key variable.
This slide introduces the structure of the table containing the coefficients for the torque equations mentioned earlier. The torque coefficient table for rotary shaft valves is organized so that values are found using row and column headers. The rows of the table are divided by valve size, and the columns represent the shaft diameter in inches. The coefficient A appearing here is the coefficient of the term multiplied by pressure in the breakout torque equation, TB equals A shutoff plus B. Therefore, the user finds the cell corresponding to their valve size and shaft diameter combination to read coefficient A and substitutes it into the torque calculation.
This slide introduces the actual numerical table for torque coefficient A. The table lists the values of coefficient A according to the combination of valve size and shaft diameter, based on the sections where the shaft diameter is 1/2 inch, and 3/4 inch if the valve size is 1/2 inch, and 3/4 inch. The values for coefficient A are presented as 0.15, 0.10, and 0.10. When the valve size is 1¼ inches, the coefficient increases to 1.80. Following this, larger size sections ranging from 1¼ 1½ 1¾ 2 1/8 to 2½ in are shown, and the coefficient values for these sections appear as 1.80 and 4.00. Additional valve size row divisions continue within the same table. In summary, the user finds the row matching their valve size and substitutes the corresponding coefficient into the torque equation.
This slide introduces the torque coefficients and maximum rotation angle for a V-notch ball valve with a composition seal. In the table, coefficients A and B are organized by size. For the 1/2 inch, size A is 0.50 and B is 0.8 and 1.8. For the 5/8 inch, size A is 0.91 and B is 3.1 and 4.7. For 3/4 in, 1.97 and 4.2 are presented, and for the larger size of 1¼ in, it is 7.3, and for 1/2 in, it is 11.7, with 12,000 appearing as the upper limit. Next, I will explain maximum rotation. Maximum rotation is defined as the angle of the valve disc or ball in the fully open position. Normally, maximum rotation is 90 degrees. That is, the ball or disc rotates 90 degrees from the closed position to the wide open position. However, some pneumatic spring return piston actuators and pneumatic spring and diaphragm actuators are limited to 60 or 75 degrees of rotation. In the case of pneumatic spring and diaphragm actuators, limiting maximum rotation allows for higher initial spring compression, which results in a larger actuator breakout torque. Additionally, since the effective length of each actuator lever changes with valve rotation, published torque values, especially those for pneumatic piston actuators, must be interpreted considering this point.
This chunk introduces the item notation part of the valve maximum torque table. In the table, maximum, M, meaning the maximum value, and TD, meaning dynamic torque, are noted. Valve torque data is organized based on the maximum value corresponding to the most severe conditions, and dynamic torque TD refers to the actual rotational force acting on the valve shaft while fluid is flowing. The units are presented in the inch-pound system, and specific torque values for each seat type are presented in the following table.
I would like to introduce the torque coefficient and separation force table for high-performance butterfly valves with a composition seat. This table is structured with the bearing coefficient B and the disc rotation angle as axes. For friction and bearing coefficients, values such as 0.11, 0.15, 1.10, 3.80, and 0.60 are presented. For the rotation angle of the disc, 18.0, 36.0, and 60.0 degrees are used. In the maximum torque area, values in the inch-pound series such as 12,000, 23,525, and 55,762 appear. Through the combination of these angles and coefficients, the bearing torque and dynamic torque are calculated.
I will now introduce the final part of the torque table and the introduction to non-destructive testing. In the table, breakout torque TB and dynamic torque TD are distinguished for rotation angles of 60, 75, and 90 degrees, and piston actuators reflect the lever length that changes with rotation in the torque calculation. Next, we cover non-destructive testing. Valves intended for nuclear service must successfully complete specific non-destructive examinations, and this may also be required by codes or customers in non-nuclear applications, particularly in the power industry. In particular, if butt welding end valves pass this examination, their rating can be upgraded from ASME standard class to special class. Special class permits use at higher pressures than allowed for standard class valves, and the upgrade procedures are detailed in the ASME B16.34 standard.
I would like to introduce a general overview of non-destructive examinations and magnetic particle surface examination. While it is difficult to cover all code requirements, this book summarizes the principles and procedures of 4 major types of non-destructive examinations defined in ANSI, ASME, and ASTM standards. First, magnetic particle examination can be used only on materials that can be magnetized. The principle involves applying a direct current across a piece to induce a magnetic field within it. Surface or shallow subsurface defects distort the magnetic field to the extent that a secondary magnetic field develops around the defect. If magnetic powder, either dry or suspended in liquid, is spread over the magnetized piece, areas of distorted magnetic field will become visible, indicating a defect in that area.
I will now cover the post-processing of magnetic particle examination and liquid penetrant surface examination. After magnetic particle examination, the piece is demagnetized by reversing the electric current. Then the defect is either repaired by welding or, if repair is not possible, the part is replaced. Weld repair is common for castings, while replacement is the standard procedure for forgings or bar stock parts. After repair or replacement, the magnetic particle examination must be repeated. The second method, liquid penetrant examination, detects surface defects not visible to the naked eye. First, the surface to be examined is thoroughly cleaned and dried. Then a liquid penetrant dye, either water or solvent soluble, is applied by dipping, brushing, or spraying, and allowed time to penetrate. Next, excess penetrant is washed or wiped off, the surface is again thoroughly dried, and a developer in liquid or powder form is applied to perform the inspection under the applicable light source.
I will conclude the liquid penetrant examination and introduce radiographic volumetric examination. In liquid penetrant testing, some developers require the use of an ultraviolet or black light to expose defective areas. If defects are discovered and repaired by welding, the piece must be re-examined after repair. The third method, radiographic examination, is a volumetric examination used to detect internal defects. The principle is that X-rays and gamma rays pass through metal objects that are impervious to light rays and expose photographic film, just as light rays would. The number and intensity of the rays passing through the metal depend on the density of the object. Since subsurface defects represent changes in material density, they can be captured via radiographic photography. The piece to be inspected is placed between the X-ray or gamma ray source and the photographic film.
Now, I will introduce the sensitivity evaluation and defect determination methods for radiographic examination in casting non-destructive testing. The detail and contrast sensitivity of a radiograph are verified by exposing a small flat plate of specified thickness, called a penetrameter, along with the test subject. This plate has several holes of specified diameters drilled into it. By observing its image on the film alongside the test subject, such as a valve body, the sensitivity of the radiograph can be determined. Radiographic examination can detect casting defects such as gas and blowholes, sand inclusions, internal shrinkage, cracks, hot tears, and slag inclusions. Particularly for nuclear service castings, certain defects like cracks and hot tears are expressly forbidden and cannot be repaired. Since the final judgment is made by comparing the radiograph with ASTM reference radiographs to determine acceptance, the experience and judgment of the radiographer play a very important role.
I would like to introduce one short requirement following the radiographic examination explained previously. If weld repairs are required for a casting, the casting must be radiographed again after the repair. In other words, a mandatory procedure follows to re-verify that the defect was properly removed by the repair work and that no new defects were created.
Finally, I will introduce volumetric examination using ultrasound. This method monitors sound wave reflections from the piece being inspected to determine the depth and size of any defects. Ultrasonic examination can detect foreign materials and discontinuities in fine-grained metal, making it suitable for the volumetric examination of structures such as plate, bar stock, and forgings. The test is normally conducted using a special oil called a coupler or underwater to ensure efficient transmission of sound waves. Sound waves are generated by a crystal probe and are reflected at each interface in the piece, specifically, at the outer face of the piece and at each face of any damaged or malformed internal portion. These reflected signals are received by the crystal probe and displayed on a screen to reveal the location and severity of the defect.
Next, we turn to noise and cavitation.
Now, I would like to introduce cavitation, flashing, and the choked flow that causes them. In the IEC liquid sizing standard, the allowable sizing pressure drop, delta P max, is calculated. The actual pressure drop across the valve is defined by the system conditions P1 and P2. If this actual pressure drop is greater than delta P max, flashing or cavitation may occur. In such cases, structural damage to the valve and adjacent piping may also result. Therefore, understanding what is actually happening inside the valve allows for the selection of a valve that can eliminate or reduce the effects of cavitation and flashing. The reason we use the term physical phenomena for flashing and cavitation is that these conditions represent actual changes in the form of the fluid media. This change is from the liquid state to the vapor state and occurs as fluid velocity increases at or just downstream of the greatest flow restriction, which is normally the valve port.
Following the previous content, I will introduce the flow schematic. It shows the situation where liquid flow passes through a restriction with an arrow indicating the flow direction from upstream to downstream. Here, the pressure upstream of the restriction is denoted as P1, and the pressure downstream is denoted as P2. This schematic leads naturally into the explanation of the vena contracta, the point where the flow cross-section is narrowest, which we will cover in the next section.
Now let's discuss the vena contracta. When liquid flow passes through a restriction, the flow stream undergoes a necking down or contraction. The point where the flow cross-sectional area is smallest occurs just downstream of the actual physical restriction. This point is called the vena contracta, as shown in Figure 5.4. To maintain a steady flow of liquid through the valve, the velocity must be greatest at the vena contracta, where the cross-sectional area is the least. As velocity or kinetic energy increases, the pressure or potential energy at the vena contracta decreases substantially. Further downstream, as the fluid stream expands into a larger area, the velocity decreases and the pressure recovers. However, the key point is that the downstream pressure never recovers completely to equal the pressure that existed upstream of the valve.
Next, I will introduce the pressure recovery characteristics of control valves and the vena contracta. The pressure differential, or delta P, across the valve is a measure of the amount of energy dissipated within the valve. Figure 5.5 compares the pressure profiles of two types of valves. One is a high recovery type, such as a ball valve, which has a streamlined flow path and high pressure recovery. The other is a low recovery type, which has lower recovery capabilities due to greater internal turbulence and energy dissipation. Regardless of the recovery characteristics, the critical pressure differential when considering flashing and cavitation is the difference between the valve inlet and the vena contracta. The vena contracta is the reduced cross-section point where the fluid passes fastest and pressure is lowest. If the pressure at this point drops below the vapor pressure of the fluid due to increased velocity, bubbles begin to form in the flow stream.
Continuing from the previous figure, I will explain the outlet pressure behavior of low recovery valves. In low recovery valves, the pressure hardly recovers after passing the vena contracta, so the outlet pressure P2 remains low. If the outlet pressure remains lower than the vapor pressure of the fluid, PV, the bubbles do not disappear and continue to flow, leading to flashing. Conversely, if the outlet pressure recovers above the vapor pressure, the bubbles collapse, causing cavitation. In other words, the extent to which the outlet pressure recovers is the key variable that distinguishes flashing from cavitation.
Now, I will explain how bubbles increase and lead to flashing damage. Figure 5 compares the pressure profiles of high recovery and low recovery valves. As the vena contracta pressure drops further below the vapor pressure of the liquid, the number of bubbles increases rapidly. At this stage, there is no difference between flashing and cavitation, but the potential for structural damage to the valve definitely exists. If the pressure at the valve outlet remains below the vapor pressure, the bubbles do not collapse and remain in the downstream system, a process known as flashing. Flashing can cause serious erosion damage to the valve trim parts and is characterized by a smooth, polished appearance of the eroded surface, as shown in Figure 5.6. This damage is typically most severe at the point of highest velocity, which is usually at or near the seat line of the valve plug and seat ring.
Now I'd like to introduce how cavitation occurs and how it causes damage. Unlike the flashing we saw earlier, if the downstream pressure recovery is sufficient to raise the outlet pressure above the vapor pressure of the liquid, the bubbles will collapse or implode, resulting in cavitation. When these vapor bubbles collapse, energy is released, producing a noise similar to what you would expect if gravel were flowing through the valve. If the bubbles collapse in close proximity to solid surfaces in the valve, the released energy will gradually tear away the material, leaving a rough, cinder-like surface as shown in Figure 5.7. If pressure recovery occurs in the downstream pipeline immediately after the valve and the bubbles collapse there, cavitation damage can extend to the adjacent downstream pipeline. Naturally, high recovery valves are more susceptible to cavitation because the outlet pressure is more likely to recover above the vapor pressure.
Next, I'll explain the principles of how to select a valve for surfaces where flashing occurs. As seen in Figure 5.6, flashing damage is characterized by eroded surfaces that are smooth and polished. To review, flashing occurs when the outlet pressure P2 is less than the vapor pressure PV. Here, P2 is the pressure downstream of the valve, which is a function of the downstream process and piping. PV is the vapor pressure determined by the type of fluid and the operating temperature. In other words, the variables that define flashing are not directly controlled by the valve. This means that there is no way for any control valve to prevent flashing itself.
Now, let's look at specific ways to minimize erosion in flashing surfaces. Since flashing cannot be prevented by the valve, the best solution is to select a valve with proper geometry and materials to avoid or minimize damage. In general, erosion is minimized in 3 ways. First, prevent or reduce the impact of particles, in this case liquid droplets with the valve surfaces. Second, make those surfaces as hard as possible. Third, lower the velocity of the erosive flow. Selecting a valve with as few fluid directional changes as possible minimizes the number of particle impacts. Sliding stem angle valves are a traditional solution that provides such a straight-through flow path, and some rotary valves, such as eccentric rotary plug and V-ball valves, also offer straight-through flow paths. Additionally, valves with expanded flow areas downstream of the throttling point are beneficial because they reduce the erosive velocity.
I'll now discuss how to choose materials for environments where erosion and flashing act simultaneously. For areas where the fluid must impact the valve surfaces, especially the seating surfaces, you should choose materials that are as hard as possible. This is because, generally, the harder the material, the longer it will resist erosion. Things become more complicated when the fluid causes both flashing and corrosion. A prime example is flashing water in a steel valve. The water causes corrosion of the steel, and the flashing then erodes the resulting soft oxide layer. When these two combine, the damage is much more severe than if either corrosion or erosion acted alone. The solution in this case is to prevent the corrosion itself by selecting, at a minimum, a low-alloy steel. Meanwhile, cavitation damage is characterized by an eroded surface that is rough and looks like cinder, as shown in Figure 5.7.
The eroded surface from cavitation is rough and cinder-like, which is distinctly different from the smooth, polished appearance caused by the erosion of flashing. As discussed previously, cavitation occurs when the vena contracta pressure is less than PV, while the outlet pressure P2 is greater than PV. Cavitation can be managed in several ways. The first method is to eliminate cavitation and its subsequent damage by managing the pressure drop. If the pressure drop across the valve is controlled so that the local pressure never drops below the vapor pressure, no vapor bubbles will form. Without vapor bubbles to collapse, there is no cavitation. To achieve this, the total pressure drop across the valve is split into smaller portions using multiple stage trims. Each of these small drops keeps its vena contracta pressure above the vapor pressure, so no vapor bubbles are formed.
The second method is not about eliminating cavitation, but rather minimizing or isolating the damage, much like flashing solutions. This method aims to isolate the cavitation from the valve surfaces and to harden those surfaces that the cavitation actually impacts. The third method is to change the system to prevent the causes of cavitation itself. If the outlet pressure, P2, can be raised enough so that the vena contracta pressure does not fall below the vapor pressure, meaning the valve is no longer choked, then cavitation can be avoided. One way to raise P2 is to move the valve to a location with more static head on the downstream side. You can also raise P2 at the valve by applying a back pressure device such as an orifice plate, but the downside in this case is that the cavitation may shift from the valve to the orifice plate.